Morning, guys. So hopefully you've had the chance to just practice through some of those kinematic equations. Pretty much is going to give you sort of some moving scenario. It's going to give you some variables, initial velocity, final velocity, acceleration, and ask you for which missing letters that you have. You're going to find that as you use a formula, you'll know you can use that formula if there's only one unknown in the problem. And usually by the time you find a new variable, let's say I just found the displacement, now I have more options in finding whatever variable that they're interested in. For today's lesson here, I'm going to introduce to you something on the side note here. This is going to be called period and frequency first. We're going to deal with this style of question, and then we're going to look at gravity as a really common example of acceleration, and we'll get back into actually practicing some of those kinematic formulas again. So, just a small, quick aside before we get back to acceleration, and that is this notion here of if I have something that undergoes what's called periodic motion. That word periodic essentially means here it's a repeating pattern. It occurs to me in cycles. And really, although cycles itself is not really a unit, it really is sort of measuring, it's something that repeats over and over again. This could be an example. Let's say I set up a pendulum. We'll deal with the pendulum in our energy option. So a pendulum basically consists of a string and a mass as a bob on the bottom here. I'm just going to pull this string backwards here, assuming perfect world here. This pendulum here will just swing to the far side, swing back. That's going to be one cycle. Swing to the far side, swing back. Now we know we live in the real world here. As it actually swings through the air, it's going to encounter some air resistance. The air resistance is going to supply some friction. This thing here is not going to infinitely go back and forth. But that can be considered a cycle. The time it takes to go all the way there, the time it takes to go all the way back. It could be a bicycle wheel. So I have a bicycle wheel here. Let's say I take a piece of tape here and I mark one spot on the bicycle wheel here. I give this bicycle wheel here a twist, so I just kind of cycle the wheel here. This masking tape here starts spiraling around. I can say one cycle is the time it takes for it to go from the top all the way to the bottom and all the way back upwards. This periodic motion, this period stuff here will be important, especially as we do waves. For waves, let's imagine like we go down to the ocean here. Let's say it's a really windy day on the ocean surface here. Maybe you are here on this boat here, and the waves themselves are just going to start zipping by you. As the waves start pushing by you here, you're going to end up going up. As the wave sort of passes by, as the wave just sort of continues onwards here, you're going to start going downwards here. You will also oscillate up and down, bobbing up and down as the waves themselves push by. Not only are waves you can see, well, the wave actually repeats itself. It's like I can just cut and paste different segments, and basically I would get all the other segments here. Definitely this is some periodic motion. All of these are examples of something that happens periodically or something that is in cycles. For motion like this, we can actually introduce, well, the time it takes for you to go all the way there and all the way back, or all the way down the wheel and all the way up, or all the way up and down and back to your regular height there. That time here, we're going to refer to that as the period. So period, we're going to use capital T to shorthand that. Period is the time for one cycle. And depending on the situation, your cycle may look completely different, right? But it's repeating, right? It's how long you need to wait, because this one here is a time. This one here will be measured in seconds. What I want to introduce to you here is not only we have a period here, I want to introduce to you another way we can frame this here. We can actually frame it as something also called the frequency. What is the frequency of the wave? What is the frequency as this thing oscillates to the far side and back? It's nice if they use F for frequency, but just a caution here, many textbooks actually use the Greek letter nu, and nu is actually like it's almost like a V with a little bit of a tail. So that's actually the nu symbol. And basically frequency, it also talks about repeating motion. It also talks about things that sort of go to the far side and come backwards. They actually have a repeating motion. But frequency, I picture it in sort of like, period is sort of, I have an infinite amount of time, right? I don't care how long it takes for you to go all the way down and all the way back upwards. Hopefully it's not that long, but I'm going to just give you an infinite amount of time, how long until one whole cycle occurs. For frequency, I sort of am impatient, and I'm sort of like, well, I'm not going to give you an infinite amount of time. I'm just going to give you 1 second, because 1 second here seems like a relatively short interval. I'm not having to wait so long. And what I'm going to do here is I'm going to figure out if I always just give you 1 second, depending on how quickly you are sort of rocking back and forth, how many full cycles do you get in the 1 second of time? Maybe you rock back and forth many times in 1 second. Maybe it takes you 10 seconds to rock back and forth. Well, if I just always give you 1 second of time, how many full cycles, what fraction of a cycle do you actually get? So a frequency here, I can just define it for you. Frequency is sort of how many cycles? It may not even be one whole cycle. It may be half a cycle, it may be 0.5 a cycle. How many cycles per? And the key here is per 1 second. I don't have all day. I'm just going to give you 1 second of time. Cycles technically itself is not a unit, so it's just going to be like, oh, I go 2 times around, so it's just 2, right? But I go per second, and therefore my units for frequency is going to be something divided by seconds. We can write this as seconds to the minus 1. That minus 1 means 1 over seconds, so that's what that means there. And if you don't really like the seconds to the minus 1 here, they actually defined another unit here. We're going to call it the hertz, HZ, in honor of hertz. And basically that just stands for cycles per second. So if I have 2 hertz, it means 2 cycles every second. If I have 10 hertz, 10 cycles per second. If you look at these two definitions here, you're going to see a lot of similarities, right? Both of them are sort of talking about a time, right? This is giving you infinite time for 1 cycle. This one here just gives you 1 second. But it also sort of relates to cycle. The relationship between these two is they're actually reciprocals of each other. So also on your formula sheet here, this is on your wave section on the backside here, we have the period t is actually the reciprocal, is actually the upside down of the frequency there, right? We can do a dimensional analysis here. If frequency is measured in the seconds to the minus 1, if I then take a fraction one more time, 1 over something in the denominator, oh yeah, that gives you seconds for period. That's called dimensional analysis, where we're just making sure the units come out as I'm expecting them. We still may be off by some proportionality constant. Maybe it's like 2 over f or 3 over f, whatever, but at least proportional as the frequency itself, let's say, increases, right? If I get more cycles every second, 1 over a bigger number means my period is actually a little bit shorter. So if you want to just sort of translate that for yourself here, by telling you that these are sort of reciprocals of each other, I'm saying the period and the frequency are inversely related. They are opposites of each other. They are upside down of each other. When one gets big, the other gets small. But I'm actually going to use this to my advantage here. Because these are reciprocals of each other, I'm always sort of in this mode of thinking a division, thinking just divide. So let's just do one quick example here. Let's use the bicycle wheel example because it's nice and easy. So we have our bicycle wheel. I'm going to tag my bicycle wheel. Let's start off 0 seconds. My tag is at the really top. And what I do is I'm just going to give my bicycle wheel a spin. This tag here is going to go all the way down, all the way up. And what I'm going to do is I'm going to try to find the period and frequency. But sometimes, just to make sure those random errors, those pesky little fluctuations here don't really affect my experiment, sometimes what I do is I leave it maybe for a couple cycles, and I just sort of average it over. Okay, well, if we went through, let's say, 5 cycles and it took 100 seconds, I can just average the times. So let's say in this question here, a bicycle wheel spins through, let's say, 5 cycles. So 5 complete sort of all the way down, all the way up. That's 1 cycle. All the way down, all the way up. It does it 5 times. Let's say it does it in 100 seconds, just to keep the numbers easy. I just want you to find or find the period and the frequency. Now, certainly, you can just sort of dissect the problem. You can say, well, 5 cycles in 100 seconds. Well, 1 cycle is how many seconds? You can sort of do it like a cross multiply. Usually what I do is I'm already thinking in the mode, well, there's going to be they're going to be sort of reciprocals to each other. What I'm going to do here is I'm just going to randomly come along and I'm just going to take one number divided by the other number. Why not? So I'm going to take, let's say, 100, right? Bigger number. What if I took 100 seconds? And what if I divide it by 5 cycles? Right? I can divide the numbers, no problem. 100 divided by 5 is equal to 20, right? And you'll notice my unit is now going to be 20 seconds per cycle. Again, the per cycle part really isn't itself a unit. It just says, okay, I just went through one of these oscillations, one of these motions here. Oh, this one here is actually measured in seconds. This is actually the time for one cycle, right? 5 cycles in 100 seconds, one cycle only takes 20 seconds. So this one here, if you look at your definitions, this guy measured in seconds is the period. During this sort of spin of the bicycle wheel here, it's twisting around fast enough so that if you give me 20 seconds of time, I can complete one whole cycle. Now what I'm going to do here is that turned out, I just randomly divided the two numbers here, that turned out to be period, and the frequency is just the reciprocal of this. You can either take the numbers the other way. You can say, what if 5 cycles gets broken up into 100 seconds? Right? So the number is not so nice, it's 0.05, but if you focus on the unit here, it says here 0.05, 5% of a cycle for every second per second. This sounds like frequency because I don't have all day. I'm just going to give you 1 second of time every time. And what I'm going to do is I'm going to wait for the wheel to actually twist around. You only get 5% of a spin every second. In 20 seconds, you would have covered one cycle. That's what we had calculated earlier. But this one here is now going to be called the frequency. This cycles here, again, is not really a unit. So I can actually list this here 0.05 seconds to the minus 1. Or better yet, I can say 0.05 hertz. If you always give me just 1 second of time, right, I don't have all day, you're only going to cover 5% of a cycle. You're only going to spin around maybe that much of the bicycle wheel in 1 second. Because it's going to take you 20 seconds to spin around once, and it's going to take you 100 seconds to spin around completely 5 times. You can verify for yourself here. They are reciprocal to each other. I just randomly came along and just put one number divided by the other. But anytime you have one of these numbers here, if I just took the period, try using your formula here, period is 1 over the frequency. If the period is, let's say, 20, and I want 1 over the frequency, I need to take reciprocals of both sides. The frequency is 1 over 20, and you're actually going to get 1 over 20. Don't leave it as a fraction because that looks precise. You round it to decimal, and then do your sig figs, 2 or 3 sig figs. So in the case of something being periodic, we can calculate these two other variables, period and frequency. Sort of a little bit of an aside from the acceleration kinematic formulas we've been dealing with. We will see this formula come back again in our waves chapter. Because waves are known to repeat back and forth, they just sort of oscillate up and down. We'll get other variables at that point there, but at least we know how to calculate the time for one cycle, the period, and then take the reciprocal of that to find the frequency. Right? Okay. So that's just a quick break from our kinematic equations here. Let's look at gravity as an example of acceleration, and then let's continue to review using our kinematic formulas. So for this section here, I'm going to refer to this as free fall. Right? Usually when things are being pulled by gravity, we say, oh, they're in free fall. Right? Nothing's, there's no rocket boosters to support them, to slow down their landing or anything like that. They're just accelerating. They're just speeding up. And this actually is a constant for our Earth. We're going to actually calculate it in the next chapter. But we'll start off here. For free fall, we're looking at the acceleration due to gravity. Because of gravity, gravity is, we're going to see, we're going to think of it as a force. Forces can cause acceleration. Forces can actually cause speed to change. And what we're going to do is we're going to pretend, again, we are all on the planet Earth. We're going to pretend we're close to the Earth's surface. Around the Earth's surface, they've actually calculated, based on how hard the planet actually pulls on you, they've actually figured out for you what is the acceleration. And the acceleration here, this is a constant. The acceleration is given to you as negative 9.8 meter per second squared. Right? And again, I'm going to qualify that for you. This one here assumes we are on the Earth's surface. Right? Assume we're not on any high altitude, we're not deep into the oceans or anything, but I'm at sort of one radius from the Earth's surface. Again, you can interpret this number here. This is an acceleration. This is talking about how quickly your speed changes. In this case here, objects fall 9.8 meter per second faster after every second. Right? Because that's what acceleration implies. Now we've started seeing, sort of in this section here for kinematics, we sometimes add a negative or we pull away a negative here. The negative just helps me indicate direction. This negative just indicates to me down. You'll notice here I just said, how come I can say positive 9.8? Well, I already implied the downwards by saying that it falls. So you're going to find us really be sloppy in this chapter. If I know the direction, maybe I'm going to just take away the negative and I'm just going to write it in words. Oh, it's a positive 9.8. It speeds up by this. But especially when you do the math there, make sure, especially when velocity and acceleration are in opposite directions, make sure you do have that negative. Right? So again, the picture I'm thinking here is, here we are, we're just standing on the Earth's surface. If I take an object here and I just drop the object, maybe I'm holding the object, maybe it starts from rest. We'll do this in the first problem here. Gravity is just ready to speed things up, negative 9.8, sort of towards the center of the Earth. In fact, in this situation here, if really I know this object has nowhere to go upwards, I might actually redefine positive actually being downwards. That way I can just use 9.8 as positive. If my velocity also comes up positive, I'm going to treat positive as downwards. So you're more than welcome to redefine positive and negative, but just make sure, especially when they're opposite to each other, make sure one is positive and one is negative. So that's sort of the acceleration case here. Sure, we say, okay, it accelerates sort of downwards. Well, you have to also sort of zoom out. What if we are actually on the planet Earth? Well, downwards for me actually means something different to downwards for a friend that's on the other side of the planet, right? For me, right, I assume, well, gravity is an attractive force. Gravity pulls masses together. I'm going to assume that any objects that I drop is actually going to go towards the center of the Earth. If my friend did the same experiment, he actually hold a tennis ball or something like that, and he dropped it, his downwards is actually going to also be towards the center of the Earth. So that's why it's totally okay for you to, oh, I'm going to redefine this direction as positive, this direction negative, because we sort of know from the picture, yeah, they're all going to go towards the center of the Earth anyways. Right? So let's just do that as a quick thought experiment here. So here we are, we're standing on a cliff of some sort. Okay, I'm holding an object just sort of off the cliff. Right now, my object here is at rest, so I'm going to say my V initial is at rest. Because gravity is constantly pulling onwards, and gravity supplies a constant acceleration of negative 9.8 meter per second squared, I know upon dropping it, objects are going to start falling. So this is right now at 0 seconds. I'm at sort of my arm level. In 1 second of time, it would have sped up from being 0 meter per second. Now the velocity here would actually be 9.8 meter per second. You can say negative 9.8 if you want, or you can say 9.8 downwards. Again, it's not like it was traveling at rest and then only for the last split second, then it goes to 9.8. Remember, acceleration is constant. Over this 1 second, it's actually speeding up to 9.8. Over the next second here, again, it's going to fall a farther distance because it's already going at 9.8. Now it's going to be going at 19.6 by the time it's 2 seconds. So this one here is 1 second, this one here is 2 seconds. Upon every second that passes by, you are only speeding out 9.8 faster than you were to begin with. So more by 9.8, more by 9.8. But again, depending on what your starting speed actually is, I'm actually going to cover more and more distance over time. So let's just try this out here. So we have this object here. Maybe the question is worded, an egg is dropped from rest. If I'm dropping it, I'm assuming I'm holding it. So I start the clock when I let go. Drop from rest and hits the ground. Not talking about the ground that I'm standing on. It hits the ground below. Hits the ground at, let's make it 35 meter per second. I want you to calculate for me. Calculate the falling time and the distance. So yes, I know upon every second it's going to travel farther and farther. Given that I know by the time the egg hits the ground, the egg is actually traveling at 35 meter per second, how long did it take to get from top to bottom? And how much ground did you actually cover? You'll notice in this question here, because I'm already starting out at the top, I'm only traveling downwards, maybe I'm going to conveniently define downwards as actually positive. So just as you don't have to, you can do negatives, perfectly works out. Maybe what I'm going to do in this problem here is I'm going to redefine downwards as positive, right? And that way I don't need to say acceleration is negative 9.8. The negative just meant downwards. And if downwards is now the positive direction, I can deal with this as positive. So again, what I want to just start introducing to you here is we're really sloppy with, oh yeah, sometimes have a positive, sometimes have a negative, whatever. But the positive negative just indicates to you direction. So let's try this out here. Again, I'm going to make a list of my variables. My V initial is at rest, so 0 meter per second. My acceleration in my new redefinition, acceleration is positive 9.8 meters per second squared. That is still implying a downwards direction. What is the 35 going in as? 35 is actually the fastest speed it's going. When I say final speed in this question, I always talk about the instant right before hitting, not after it smushes, after it slows down, after it sort of collides and bumps and stops. I'm not talking about that final speed. I'm talking about the final speed. I'm going to write this down for you here. The final speed is right before the impact. So the final speed should be the fastest this egg travels before it's going to actually hit the ground. So this is actually V final. Again, V final was a downwards direction. It should actually be negative 35, but seeing as I've redefined downwards as positive, I'm actually going to say 35. If you think back to sort of the truck and airplane questions we've been doing, imagine this is your runway. Imagine we start off here from rest and we gradually accelerate over the runway. We can say it's a positive runway, a positive distance, even though downwards is typically negative. Right? Notice that we do have an acceleration. So again, I'm thinking right away either v is equal to v naught plus at, the d is equal to v naught t plus 1/2 at squared, or the v squared is equal to v naught squared. All three of these formulas work, but again, whichever formula you use, you have to know basically all of the variables except for one. Right? If you have more than one unknown, you can't really use that just yet. So again, I'm just going to highlight through here my v initial. Great, I know v initial. Even if v initial was not 0, you just punch in the v initial there. I know the acceleration, and they don't actually have to tell you the acceleration, by the way. If you notice that, oh, it's gravity that's pulling it down, you can actually just treat that as a constant. That's a constant on our Earth's surface. And then, in this case here, we have the final velocity. I mentioned to you last day, the first and the third formula there, those deal with final velocity. Oh, great. If you're interested in finding the time, maybe this formula will work, because that's the one unknown. I can't quite use this middle formula just yet, because I don't know d or t. But once I find the t in this first step, maybe I can punch it in to solve for d. Or better yet here, if I don't need to rely on t at all, well, I know final, I know all these other numbers, I know the displacement. Maybe I'm going to use these two on the far side here. So let's just try it through here. I redefined downwards as positive. So if I want to get to a speed of 35, my starting speed is 0. My acceleration is going to be 9.8. Again, you might say, wait, I thought it was negative 9.8. Remember, I had redefined downwards as positive. And you don't really need to write that out. It's just I'm just putting that for you just for convenience here. We're going to look for the time. So this is going to be 35 is equal to 9.8 times t. And therefore, your t is equal to 35 divided by 9.8. This gives you here, give or take, 3.6. Remember, in physics, just keep everything 2 or 3 sig figs. I could totally, now that I know the time, I could totally punch that into the middle formula. I'll leave that for you to check later on. But just in case I got my time wrong, in this case here, let's just try the last formula. Well, I'm supposed to get up to 35. They want you to take 35 and square it. 0 and square it plus twice. 9.8 times the d. Sure, we need to do a little bit of manipulation here, but still not too bad. 1225 is equal to 19.6 d, and d, so 1225 divided by 19.6 gives me here a distance of 62.5. So double check, again, I talked about sig figs, 2 or 3 sig figs. Make sure your final answer also have units. And therefore, oh, this is actually a positive distance. But remember, in this question, I just keep coming back to this here. In this question, I define positives downwards. So if gravity pulls downwards 9.8, if your final speed is 35 downwards, you will have traveled a distance of 62.5, and it would have taken you a positive 3.6 seconds to actually fall downwards. This actually gives us a very interesting way of actually finding the height of an object. Imagine you were reaching over an elevator shaft and you wanted to figure out, well, how sort of far up from the bottom of the elevator shaft I am. What I can do is I can drop an object. I'm not saying do this experiment, but I could. I can drop this object here. I can just have a stopwatch from the time I drop it to the time that I hear it collides at the bottom. Because I know the acceleration rate is actually 9.8, as long as we're on the Earth's surface, as long as my elevator is actually on the Earth, I can just do a simple division there, and this can actually help you find displacement. It can even help you find final velocity if you were interested in that case there. All right. I'm going to introduce to you sort of one last setup here. It doesn't look like a free fall question, but as we sort of dig into this here, you're actually going to see, yes, it's more similar to what we've been doing. So what I'm going to do here is I'm going to be standing, same idea here, but I'm going to be standing sort of over a ledge. And this time, instead of just holding the object and just dropping it, this time I'm actually going to toss the object upwards.
So let's just write this down here. An object is thrown upwards at, let's make it different. Let's make it 15 meters per second. So I know just sort of experimentally what goes up has to come down. It'll gradually go up. It's going to hit some peak height. That's what I'm going to be interested in. And it's going to start coming back downwards. Because I'm sort of standing over a ledge here, as it falls, it's actually going to fall kind of past me. Let's say I was standing on a dock here. I'm not interested in it hitting the dock where I'm standing. I'm interested in it hitting the ground below. And in this case here, let's say the dock here is 30 meters high. In this case here, your pictures will be really helpful because especially as you're making a list of variables, depending on which situation that you're looking at, your variables might look a little bit different. Right? So I'm going to separate this question into two parts. That's all I'm giving you. So an object is thrown upwards at 15 meters per second. The first part of this question asks you about a max height. So A is right here. So for a max height question, the question is worded, how high does the object get and how long until it reaches the peak? Right? So even though the wording is a little bit hard, well, how high is talking about a distance. It's talking about, well, from where I'm starting to throw it, what is this distance here? How far off the dock does it get? And also how long is asking you for a time. So you can sort of dissect that for you there. Right? I'm going to come back to that blindfold on, blindfold off analogy here. I'm going to start off here. My blindfold on part is my initial point here. That's when I actually start throwing the object upwards. I throw it upwards at 15 meters per second. I'm going to take off my blindfold when it is up here. So this is my final condition. When I make a list of variables, I'm going to do my V0 and my V final for those numbers here. And what I want to factor in here, it doesn't seem like we have enough information. Now again, what's understood here is, well, it's gravity that's slowing it down anyways. What's going to happen if my velocity is upwards? I throw it upwards, but gravity doesn't care you're trying to toss it upwards. Gravity is trying to accelerate it in the negative direction. We had seen that anytime these two are opposites of each other here, we know that it slows down. That means we're going to go from 15, we're going to gradually get slower and slower, 10, 5, 4, 3, 2, 1. What is my speed at the really, really top? In fact, the maximum height, the reason why I actually come to a stop is because my V final here is actually 0. We actually are at a rest if we're at the top. When I take my blindfold off, you're not traveling upwards anymore. That's the maximum you're ever going to reach. So if I make a list of variables just for this sort of part A of the problem, I can say my V initial is 15. This time positive means upwards, like normally. That means my acceleration has to be negative, so negative 9.8, because I want to imply that those are two different directions. Earlier we were just falling, and I just redefined downwards as positive. This case it will be important. And now I actually have the V final. The V final is actually 0. You can make a note to yourself. You have stopped moving at max height. Right? That's when you're when you've reached a peak. And now I have these variables here. I can pretty easily find the other variables. I have an acceleration, so I'm not going to do a basic motion equation. This one here assumes that there's no acceleration. It doesn't really help me. So what we're going to do instead is we're going to use our kinematic formulas. As you get more familiar with it here, so maybe I want to do, let's say V is equal to V0 plus AT, right? So let's just punch it in here. My V final, I know it to be 0. My V initial was 15. They didn't have to tell you, oh, by the way, it's gravity is pulling down. I'm assuming it's gravity is pulling down. So I just memorize that number as 9.8. I can find the time in this fashion here. So I'm going to bring the 15 over. Negative 15 is equal to negative 9.8 t. T should always come out as a positive. So if I go 15 divided by 9.8, this gives me here 1.5. So because I know gravity is slowing it down at 9.8, it's going to take gravity about 1.5 seconds to bring it to a stop. And at that point there, I can find the displacement. Earlier, I had used the other formula, like, oh, I don't want the time being wrong to knock off this answer here. I'm going to show it to you. Hey, that formula works. The more you know, sort of the more options you have. Now, careful, you might say, well, I know a D. D is 30. But you'll notice in this situation here, I haven't even dealt with this falling part just yet. I don't care about I'm standing on a dock. If I was just standing on the ground and throwing it upwards, I would still hit some distance that's actually up from where I'm standing. So just from your formula sheet here, d is equal to v naught t plus 1/2 at squared. Again, you're more than welcome to still use vi and vf. Just make sure you know which term is which. In this case here, I'm throwing it upwards at 15. If I can keep my number unrounded, that 1.5 number, plus 1/2, my acceleration is against me, so negative 9.8 times it by 1.5 squared. Just crunch your way through the numbers there. 15 times this answer. That gives me here 22.959, give or take. I'm going to type in the 0.5 times 9.8 times 1.5 squared, give or take a little bit of rounding here. The other number gives me roughly 11.025, and therefore, you normally don't need to show that work there, but I'm just going to demonstrate that for you here. I might be off by a little bit of rounding, but my distance that I'm getting is 11.5 meters. And notice that this one here is a positive. What does that mean? That positive means we actually reach 11.5 meters higher than, I'm going to call it the launch point, than when I stood. And you notice that this 11 is irrelevant to the height of the dock, right? If I was just standing on the ground, I'm still going to reach 11 meters up. If I had said how far off sort of the water, how much elevation do I have, then you would need to factor in, oh, I'm actually 30 meters up already. 30 plus 11, oh, I'm actually 41 meters up, right? Now, what's interesting about this question, I'm going to leave you with this problem here. What's interesting here is because this is only part of the motion, I can now ask you for the second part of the motion. For the second part of the motion, as implied, it's going to slow down, slow down, slow down, slow down until it comes to a stop. It's going to actually start speeding up, going downwards. Now that your speed is actually downwards and the acceleration is also downwards, we know that means we're going to speed up. So we're going to go from that having stopped at 0, we're going to start going -5, -10, -15, or whatever. The negative just implies direction. You can even do a calculation for yourself. By the time it actually passes you, it's actually going at -15. What I want to do here is, if you give gravity an extra 30 meters worth of distance to speed this up, I want you to actually calculate for me what's the final speed right before hitting. Again, not the speed after it hits the water and slows down and loses all its momentum and all that. I want the speed right before hitting. You can totally reset initial and final wherever it's convenient. So if you do blindfold on, blindfold off as an example, you can say, let's imagine I start off like 41 meters from the ground. Initially, you're at 0. I'm going to fall a total of that 41 meters. You can put your blindfold on here. You can take your blindfold off here. But for me, I'm going to be a little more clever here. I'm going to say, well, what if my part A was off? What if all these numbers here have been wrong? I don't want my part A actually knocking off part B. So what if I still kept my blindfold? I put my blindfold on when I tossed it upwards. I'm going to keep that initially the same. But what I'm going to redefine, I'm going to have my blindfold on. I'm going to assume it hits some peak height, but I'm not watching it. By the time I take off my blindfold, it's actually fallen 30 past me, and I'm going to take my blindfold off afterwards. What if I did something similar? I made a list of my knowns. I made a list of all my numbers. But what if I did it for start here, and my final velocity would now be unknown because I'm not at 0 anymore. I redefine initial and final to where it's convenient for me. So let me just sketch you a picture of this. So far we know this object here is going upwards at 15 meters per second. I have my blindfold on for the entire all the way up and all the way down motion. I know this is going to travel 30 meters, and I'm going to take out my blindfold down here. I don't know what my final velocity is. Right? So let's make a list of my variables. So part B. So let's consider the entire motion. So consider not just all the way up and just stopping at peak height. It doesn't stay there just for an instant, but consider the entire motion. So from the time that I launch it to the time that it actually hits the water below, let's make a list of the variables. Initial velocity hasn't changed. Initial velocity is 15, positive. Acceleration hasn't changed. Acceleration is negative 9.8. That's opposite it. That acceleration here is slowing down my velocity. It's bringing the object here to a rest, and it's also speeding it downwards. This time, your VF, I don't know. Earlier, we said the VF was 0, but that VF was 0 only at the max height. I'm totally blindfolded for this part here. I'm totally past the max height question. The VF is actually the fastest speed. I don't know the speed anymore. Again, this one here is actually the speed right before impact. Right? It's the fastest speed. It's no longer 0. again, it seems like I don't have enough information. Now the 30 actually comes into play here. This 30 here is actually 30 meters. From when I have my blindfold on to when I have my blindfold off, you notice that I actually am 30 meters lower than where I started. I actually know the displacement this time. It's not the 11.5 that I calculated. That 11.5 was just the motion going upwards. But the displacement I can put in is when I take my blindfold off, I look back upwards. Oh, I'm actually 30 meters lower than where I started. Punch in a D of negative 30 meters. Again, it seems really sloppy. Why did I just suddenly add a negative? That negative just implies here. This one starts off, I'm 30 meters lower than the dock. And it has nothing to do with the 11.5. I could care less that I actually went up and went down because that totally sort of canceled out. I have my blindfold on for that whole time. I don't know. All I know is from start to finish, I'm actually 30 meters lower. So try your kinematic formulas here. I'm going to leave that for you to try. I want you to calculate. So again, this is part B of the question. I want you to calculate the total, we call it the flight time. The total time that's in the air from when I launch it to by the time it gets down, and calculate the final velocity. Again, you might say, oh, I thought it was 0. It's 0 for the max height question, but it's definitely not 0 because it's actually going to be accelerating. It's actually going to be traveling really, really quickly right before hitting, and that's actually the speed we deal with for kinematics. All right? So give that one a go, and we'll pick it up from there. Thanks, guys.